All right, so let's talk about the law of conservation momentum. So, when we say that momentum is conserved, what we're talking about is that in an isolated system, and by isolated system, we mean that it's a system that is not being affected by external forces. The total momentum remains constant. Yes, the momentum of each individual object interacting can change, but the total amount of momentum within the system needs to remain constant, right? Otherwise, you have some magical force interacting, right, changing the momentum of these objects, right? So, in an isolated system, again, in the absence of external forces, the total momentum of your system must remain constant, right? We do not believe in magic here. So, what we're saying is that P naught equals P. Right? Your initial momentum has to equal your final. Or, if we want to expand this into, let's say we have two objects interacting, mass 1 times V naught 1 plus mass 2 V naught 2 has to equal mass 1 final velocity 1 plus mass 2 final velocity 2. Again, your individual velocities here for your masses can change, but the overall momentum of the system, as long as it's not being affected by external forces, needs to remain constant because otherwise magic has been done. So, for instance, let's take a look at example 9.5 on the notes. So you've got two ice skaters, Sandra and David. They stand facing each other on frictionless ice. Sandra has a mass of 45, David has a mass of 80 kilograms. They then push off of each other. After the push, Sandra moves off at a speed of 2.2, and we want to know what David's speed is. So, again, you always want to start any problem that deals with conservation with this explicit statement that momentum is conserved. There's always a point associated for just saying your initial momentum equals your final. Don't be lazy and skip down to another step because you're going to be losing out on a point there. So, our initial momentum equals our final. Now, in this case, we've got two people. I'm going to call mass Sandra, velocity Sandra, mass David, velocity David. Put V naught, V naught is going to equal to mass Sandra, final velocity Sandra, plus mass David, final velocity David. Now, these two ice skaters initially are just standing there facing each other. Right? They're not moving. So each of them has a velocity of 0. So we know that the total initial momentum is 0 kilogram meters per second. Now we know that Sandra moves off at a speed of 2.2 meters per second. So she's got a mass of 45 kilograms times 2.2 meters per second. We know that David has a mass of 80 kilograms. And we want to know David's final velocity. Now, keep in mind, they're going to be moving off in opposite directions. So one will have a positive velocity, one will have a negative velocity. Unless it's explicitly stated which one is moving in the positive direction, which one is moving in the negative direction, it doesn't matter which one you assign. So I'm just going to put Sandra as positive just because they didn't specify which one was going which direction. So 45 times 2.2 gives us a momentum of 99 kilogram meters per second. Plus David's mass times his unknown velocity. Right, we move over that 99. And then divide out that 80 kilograms. And we get that he has a speed of, let's say, 1.24, and that is negative. Now, you always want to do a gut check on these types of questions. Now we know they're moving opposite directions, so good. He came out negative when she's got a positive velocity, so that checks out. You did your algebra right there. Also, you know that if she's moving with a certain speed and she has a lesser mass, well, he's got a greater mass. He better be moving with a lesser speed. Right? If he had come out with some speed greater than hers, you should probably go back, check your algebra. You know you done something wrong. All right, now let's take a look at the next example in the notes, example 9.6. So here we've got Bob. He's running from the police, thinks he can make a faster getaway by jumping on a stationary cart in front of him. He runs towards the cart, jumps on, rolls along the horizontal street. Bob has a mass of 75 kilograms, and the cart's mass is 25 kilograms. If Bob's speed is 4 meters per second when he jumps onto the cart, we want to know what is the cart's speed after Bob jumps on. So again, you always want to start with an explicit statement that momentum is conserved. And actually, let's say this was a free response question and you had no idea how to do it, but you know that it deals with conservation of momentum. At the very least, write on the paper, momentum is conserved. Get yourself a free point on that free response question. All right, so just a little aside. All right, so we got two objects, Bob and the cart. So we got mass of Bob, initial velocity of Bob, plus mass cart, initial velocity cart. And that's going to be equal to the mass of Bob times the final velocity plus the mass of cart times the final velocity. Now, there's a reason I didn't subscript this final velocity. Think about what's happening. Bob jumps on the cart. So Bob and the cart must be sharing a final velocity. All right, so let's go ahead and continue with this. So mass Bob, V naught Bob. The cart has initial velocity of 0 is equal to the mass of Bob plus the mass of the cart times the final velocity. So you can always skip this step right here and go straight to here because we know that Bob and the cart are being treated as one object, right? Bob is riding the cart, they have the same velocity. So let's go ahead and fill in what we know. Bob's got a mass of 75 kilograms. And we know he has a velocity of 4 meters per second when he jumps on. Now we know Bob still has a mass of 75. We know the cart has a mass of 25. And we want to know final velocity. All right, so solve this guy out. And you get a final velocity of 3 meters per second. Right, and you, again, gut check your answer. That makes sense because Bob had some amount of momentum, the cart didn't. When he jumps onto the cart, you have the same amount of momentum, just now you've got a greater mass there, so your velocity needs to go down. Right, so if Bob was smart, he would never have jumped onto that cart. All right, now, so there are a few different scenarios we can deal with when we're dealing with conservation of momentum. And the first one is explosions. So basically, what we're talking about when we're talking about an explosion is that you have an object that is torn apart due to some internal force. So that example with Sandra and David on the ice pushing off of each other, we would consider that an explosion scenario because you've got a single object, in this case it was Sandra and David, there's an internal force there, they push off of each other, right, and they're torn apart into opposite directions. Now, the best example we have of that, and again, think back to when we were talking about Newton's third law, because explosions and Newton's third law go pretty much hand in hand, is a rocket ship, right? Look at what happens when you're dealing with a rocket ship. Well, let's say the rocket ship is at rest initially, right? You've got your fuel on board. It initially has a total momentum of 0. Well, what happens when it ejects these exhaust gases out the back? Well, there's an internal explosion there, right? And momentum, or the exhaust gases, right, are given some momentum backwards. Well, the law of conservation of momentum says that the total momentum must remain zero. So if suddenly these gases gain negative momentum, this rocket ship must gain an equal amount of momentum in the positive direction. Now, obviously, the gases have smaller masses and higher velocities, and the rocket ship will have a larger mass and a slower velocity, or a lower velocity. But again, that overall momentum must equal zero if momentum is to be conserved, right? And that's how rocket ships work. Right? It's the same way with, say, your squids, or the scene in WALL-E we talked about during Newton's third law, where he's got the fire extinguisher. Right? Same idea there. Momentum must be conserved. If there's momentum granted this way, the other object must get the same amount of momentum the opposite direction. So let's take a look at another example of a collision. Or, sorry, an explosion. So, in example 9.7, we've got ourselves a 30-gram ball. It's fired from a 1.2 kilogram spring-loaded toy rifle with a speed of 15 meters per second. And we want to know what is the recoil speed of the rifle. Well, again, always start with an explicit statement that momentum is conserved. Now, we know that initially, neither the toy rifle nor the ball are moving. So we know that there is zero total initial momentum. And that the ball will have some velocity and the rifle will have some recoil velocity in the opposite direction. Alright, so let's go ahead and plug in our figures. So again, make sure that you are not working in grams. Always check your units there. So 0.03 kilograms times 15 meters per second plus 1.2 kilograms times that unknown recoil speed has got to equal 0. Alright, so do your math here. And you get a recoil speed of negative 0.375 meters per second. Again, you want to do a gut check. If one is going in the positive direction, the other's got to be going in the negative. If one has a larger mass, it should also have a lower speed. So, take a look at question 9.5 and stop to think in the notes. We've got an explosion in a rigid pipe. It shoots 3 balls out of its ends. A 6-gram ball comes out of the right end. A 4-gram ball comes out of the left with twice the speed of the 6-gram. And we want to know from which end, left or right, does the third ball emerge. So go ahead, pause the video, and see if you can't work that out. Alright, easiest way to look at this is sketch out your scenario. So we've got ourselves a pipe. Out of the right end, we know that the 6-gram ball comes out with some speed we can call v. Out of the left end, we've got a 4-gram ball coming out with a speed of 2v, right, which would give it 8v worth of momentum. Now, initially, the momentum of this system is 0. So we know that at the end, the momentum also has to be 0. So if you have 8v worth of momentum coming out the left, and you have 6v worth of momentum coming out the right, we know that overall, there needs to be 2v worth of momentum more coming out the right. So that we know that the third ball has to make up this extra 2v. So that third ball has to exit through the right of the pipe. Alright, so now let's talk about collisions. You have two possible types of collisions. They can either be elastic or they can be inelastic. Elastic collisions mean that the objects bounce off of each other. So a good example of that would be playing pool. Right, you hit the cue ball hits the 8 ball, they all bounce off of each other. Or playing croquet. Um, Now, your inelastic collisions mean that the objects stick together. So things like a car accident, or a bullet embedding itself in a piece of wood, or someone tackling someone. So your collisions fall between either elastic or perfectly inelastic. Now, keep in mind though that there really is no such thing as a perfectly inelastic collision. Typically, your collisions fall a little bit between there in a little gray area. But again, you've got to treat things as either or sometimes to make sense of the world. Um, so for our purposes, we treat things as either perfectly elastic or perfectly inelastic for the most part. You just got to realize in the back of your brain that that's an ideal, right? You can get close to that, but things fall a little more in the gray area usually. So let's take a look at an example of a inelastic collision. Now we already saw one earlier with Bob jumping onto the cart. Um, and what do we notice there? Well, when Bob jumped onto the cart, they stuck together, right? And they were treated as one object at the end. So in your inelastic collisions, these objects move with the same speed, right? They're treated as a single object moving. So in example 9.8 in the notes, we've got a train, two of the cars with masses 2 times 10 to the fourth kilogram and 4 times 10 to the fourth kilogram are rolled towards each other. When they meet, they couple and stick together. The lighter car has an initial speed of 1.5 meters per second. The collision causes it to reverse direction at 0.25 meters per second. We want to know what was the initial speed of the heavier car. Well, again, start with an explicit statement that that momentum is conserved. Now, we have two carts going towards each other. I'll call it light cart and heavy cart. So, subscript L for light, subscript H for heavy. And we know that they couple together and travel at a single speed. Again, they give us no indication of which one is rolling in the positive direction, which one is rolling in the negative, so I'm just going to make the lighter one moving in the positive just because why not? So we've got 2 times 10 to the fourth kilograms times 1.5 meters per second plus 4 times 10 to the fourth times our unknown initial, and that is equal to 6 times 10 to the fourth times negative 0.25 meters per second. Now, the reason I made this guy negative is because they tell us that the collision causes the lighter cart to go in the opposite direction. Right, so the lighter cart was initially going in the positive, now it's going in the negative. So, go ahead, do your algebra. And you should end up with an initial velocity of the heavy cart as negative 1.125 meters per second. Right, again, that answer makes sense. You got negative for the direction and a lesser speed. Now, the last thing we want to look at is this stop to think question 9.6. So you got two particles shown collide and stick together. After the collision, the combined particles, and then you got options, move to the right, move to the left, are at rest. So take a second, pause that video, see if you can't figure out how to solve that question. So easiest way to look at this is we should figure out what the overall momentum was initially, because that's what we know the overall momentum will have to be finally, right? Because again, we know that energy is conserved. So initially, object 1 has a momentum of 0.4 kilograms times 2.5 meters per second. So object 1 has momentum of 1 kilogram meters per second. Now object 2 has a mass of 0.8 kilograms, a velocity of negative 1.5 meters per second. Again, negative because it's moving the other direction. So we know that its overall momentum is negative 1.2 kilograms meters per second. So we know by looking at this that overall there's an initial momentum in the negative direction, right? So we know that if it initially has negative momentum, its final momentum also has to be negative, right? Unless some outside force came in and delivered an impulse. So we know that the objects have to be moving to the left. Now, as far as the rest of the notes go, we're going to skip collision in 2 dimensions because, frankly, we're trying to catch up time here. I'll make a video at some point, just in case you have extra time to take a look at it. And as far as energy and collisions, we'll cover that mostly when we get to energy next semester. We had to kind of reshuffle the order just because of a time crunch. But the big thing to know, at least for now, is that when we're talking about inelastic collisions, kinetic energy is not conserved, and that all of that energy becomes thermal energy, which is heat. So as long as you are comfortable with that statement, you should be good for understanding energy and collisions for now. Is that when you have things that ram together and stick together, you have a lot of friction there, right? And that friction, just like when you rub your hands when it's cold, generates thermal energy, heat, right? So inelastic collisions are not energy conservant. Um, but again, we'll cover this when we get to energy. Um, but again, just know that energy is not conserved in inelastic collisions for now. Um, so yeah, you got questions? Yeah, come on down to the live engagements. We can talk about them.